we're given position function s of t, 0.04 t squared plus 3t plus 7. And we're asked to find the average rate of change of position with respect to clock time between t equals 2 and t equals 3, then between t equals 2 and t equals 2.1, and then between t equals 2 and t equals 2.01. We're not going to do the 2 and the 2.1. That's very easy to do, and if you don't understand how to do that, you should, having seen how to do this. And this is really something that's pretty redundant with what we did in the last class, but we want to incorporate this into the context of slope, rise over run, tangent line. Be sure that we really understand this idea and the idea of rate of change and how it's related ultimately to derivatives. So the average rate of change from t equals 2 to t equals 3, well, it's the change in the position divided by the change in the time. So we find the position at time t equals 2, s of 2, and we plug 2 in here, we get 3.16. We plug in 3, we get 16.36. You can do the plug-in and verify this. So here's your position at t equals 2, here's your position at t equals 3. The change in position is, well, you subtract the initial from the final, you get 0.20, and it's not 0.20, it's 3.20. And that's written so badly I need to fix it. Okay, so the change in position is 3.20, and the change in time is just from 2 to 3. The change is 3 minus 2, which is 1. Thus, the average rate is change in position divided by the change in the clock time. 3.20 divided by 1 is 3.20, and that's the average velocity between 2 and 3 seconds. Now, between 2 and 2.01 seconds, what's the average velocity? Well, we already know what the position is at t equals 2. It's 13.16. If we plug 2.01 in, we get 13.191604. Now, this is a little strange if you're a physics student because we've got way more significant figures than our information permits, but we're assuming an ideal case where everything is completely accurate. Okay, doesn't correspond to physical reality, but this is an ideal reality that we're talking about here. Okay, so our change in position there is about what? It's about 3.1916. I left off the 04, but since I then included it in this calculation, I probably should have, so let me sneak it in there. Okay, 3.191604 minus 13.1604, and that gives us a 0.03. And my decimal, it's there. There's my decimal point. Let's make it a little bigger. Equals 0.031604, and that's the difference in the position for this hundredth of a second interval between t equals 2 and t equals 0.01. Now the change in the time is there, clearly a hundredth of a second, or a hundredth of a unit. We didn't say what the units of these things are. So we get delta S over delta T is this change in S, change in position, divided by the change in time. That gives us 3.1604. And that's a little bunched up, so I'm going to kind of fix that. And that's the average velocity for this interval. Now we see that the average velocity on the 1 second interval is 3.20. The average velocity here is 3.1604. And then we calculate the instantaneous rate at which this position is changing, and that's simply the derivative, s prime of 2. Now, we can, and I wrote it over here, s prime of t is 0.08 t plus 3, just taking the derivative, and we know how to take that derivative. Okay, t squared has derivative 2t, 0.04 times that gives us 0.08 t, plus 3 times the derivative of t. The derivative of t is 1, so it's 0.08 t plus 3. And we plug in 2, and we get exactly 3.16. So we see how these average slopes are approaching the instantaneous slope, 3.16. Now again, what's that mean in terms of the graph? Well, our first interval goes from 2 seconds to 3 seconds. The run is 1, and again I'm saying seconds, from 2 to 3 time units, whatever those units are. The run is 1 time unit, and the positions, okay, this is position versus time, of course. This is S versus T. The position goes from 13.16 to 16.36. So the rise is this, and of course that is your change in position, and your run is 1, that's your change in clock time. So the slope is 3.20, that's the rise over the run. And that's 3.20, and that is delta S over delta T, because the 3.20 we identified as a change in position, and the 1 we identified as the change in clock time. Now, if we go from 2 to 2.01 on the T axis, what happens? Well, of course, these points are much closer than they're indicated here, but we get a very tiny triangle with a run of 0.01 from 2 to 2.01. I probably ought to put parentheses around these numbers just to distinguish them. The run of 0.01, and evaluating the function, we get the corresponding values of the position, which is on the vertical axis, 13.16, 13.191604, and we get a rise of difference of these two, 0.031604. The meanings are the same as they are up here. The rise represents change in position, the run represents change in clock time, so the rise divided by the run is the average rate of change of position with respect to clock time. That's your slope, and this is what we get, and that is a representation of your average velocity, as this was a representation of the average velocity on this bigger interval. Now, if we do a tangent line, the slope of the tangent line is the instantaneous velocity. It's the 3.16 that we get here. Now, we need to understand how the rates of change are represented by a graph and a rise divided by a run, so we can understand the meaning of the slope. In this case, that meaning being the average velocity, the rate of change of position, the average rate of change of position with respect to clock time, or in this case, the instantaneous velocity, the rate of change of position with respect to clock time when the time is 2.